let's see what we can do if we can find a few interesting problems and what we'll do about attempting to solve them. So first up, in no particular order, mind you, we have what you guys will come to find next term if you haven't done this already, which is the annuity, a formula for the future value of an annuity. This x is an installment, and this is the calculation, but it's asking us to make n the subject of the formula. So basically, let's get going. So first issue is that I, and we multiply both sides by it, so we'll have I multiplied by f being equal to x square bracket, and then we'll have 1 plus I to the power n, and this 1. There you go. Okay, so let's divide both sides by x. What we do to the left, we do to the right, vice versa. So that has that effect, which is good. So we now have, well, I times f all divided by x being equal to, well, we can get rid of these square brackets now. That was the point of dividing by x. So we're left with 1 plus I all to the power n minus 1. Well, this one's easy. We're adding 1 to both sides. So now we have I times f divided by x plus 1 being equal to, well, 1 plus I all to the power n. Well, what can we do now? Well, given that this n is what's meant to be the subject of the formula, we can now apply our log definition. For that, we need to look at the expression on the left as one term, which is why I just put it in brackets. Radio. So remember how we deal with logs. The answer to a log is an exponent. Radio. So what does that mean? Well, n is going to be our exponent, and that has to have a log. Well, what's the base? Well, the base in the exponential form is also the base in our log form, and then that expression becomes our argument. So let's deal with that. So we'll have I times f all to the power, all divided by x plus 1, and that is as simple as that is. So what was the value of this, Mr. K? Hey, quite simply, it's just basically to illustrate the simplicity of equations in what's required, regardless of what the operation was right through when we were changing the subject here to get n to be the subject, or to get it to say n is equal to, well, we kept doing the same thing to the left and the right, regardless of what the operation was. So first, we multiplied both sides by I, and then we divided both sides by x, and then we added 1 to both sides, all until we could get our subject as alone as possible. Then and only then did we switch forms, because it was in the right form, being one expression on the right, one expression on the left, and that exponent n forced us into our log conversion. So easy, maybe, maybe not. Simple, definitely. Don't confuse the two. Move right along. Seems like we have a mixture of concepts over here. Left the mark allocation intact. So what do they want? They want us to solve for x if, well, the summation from the third to the fifth term of the general term x to the power k minus 2 is less than, well, 7x. So let's take care of our sigma notation over here, our summation as given in sigma notation. Well, it's just terms 3, 4, and 5, so we might as well calculate those on their own. So where k is equal to 3 we shall have x to the power 3 minus 2, which is just equal to x, for k equal to 4. Well, we can see where this is going. That's just going to be 4 minus 2, so we'll have x squared. And then where k is equal to 5, we shall have, well, x to the power 5 minus 2, which is just equal to x cubed. Well, so this summation can be rewritten as x cubed plus x squared plus x being less than or equal to 7x. And then we can even rewrite that further and state it as, well, x cubed plus x squared minus 6x, and that's if and only if we apply the correct technique. If we do to the left, we do to the right. Well, that should be minus 7. Let's not confuse myself and others. Well, if we can have a look at that, we can factorize what's on the left. That just becomes x. Then we'll have x squared plus x minus 6. That's still less than or equal to 0. We'll have x, and we'll have x minus 3, and then x plus 3, x minus 2, well, less than or equal to 0. Well, radio. So when we have more than 2 terms, for our critical values, we still have 0 from that first factor, x being equal to negative 3, and then x being equal to 2. But for this one, a tabling method is going to be a bit more appropriate. What do you mean by that, Mr. Markham? They've never shown us a table method. Well, let's just have a look at that then. Well, firstly, we can have well, x plus 3 x minus 2, and then just x. Well, these are 3 factors, and we'll call this just f of x. That's when everything gets multiplied together. So how does this table method work? Well, quite simply, we have a look at all our factors and we construct a number line at the top. I'll put a 0 somewhere. That's 0. And that happens to be where x, that critical factor, or that critical value lies. Then there's also a critical value at minus 3 for this one. So that's going to be minus 3, it's going to be 0, and yet another critical value at 2. So now we go row by row. For x plus 3, the critical value is at minus 3, which means everything to the left of that is negative, and everything to the right of it is positive. Why? Because everything to the left of negative 3 has to be negative, because this is where this factor makes this expression equal to 0. Radio. For minus 2, the critical value sits here. This is where it turns this expression into 0 again. So everything to the left of 0 is negative, and everything to its right is positive. And then for x is quite simple. Where x is equal to 0, everything to the left is negative, and everything to the right is positive. How do we do this now? Well, when we go into the downward direction, we multiply everything. So negative times a negative times a negative just gives me a negative. Then we have a positive, because we have 2 negatives multiplying, giving us a positive. And then for this, 2 positives and a negative gives us a negative. And then we have a positive over there. So we can see, given that we want less than or equal to 0, everything over there and everything between those two values. Now it's just a case of tracking them for our solution. So x should be less than or equal to -3, or x should be greater than or equal to 0, less than or equal to 2. That's how that works. Well, isn't there a graphical method for this? Well, let's have a look. Okay. Let's leave that alone. Okay, we've created enough space now. Remember, our graphical method depended on us knowing the shape. Our leading coefficient had to be positive, as it is over here, and we know for any cubic, if we want to draw the graph of it, we needed to know the general shape based on the value of a, and we know for any cubic if the a value is greater than 0, then the cubic looks like this. Let's see what happens if we put our values in order. So that's going to be -3, that's going to be 0, and that's going to be 2. What do we want? Well, we want the values that are less than or equal to 0, because this is our x-axis, and as we can see, it's that area and that area. So as we can see, we can extend the concept from parabolas to cubics, because x ends up being less than or equal to -3, or x is greater than or equal to 0, less than or equal to 2, and these two concepts just match. So that's the extension of a concept. So if you understand the theory behind it, it's not that difficult to extend the concept to a slightly higher degree or to deepen your theory. Then hopefully you learn something new. Now, for which values of k will the summation to infinity from the first term of 3/2 minus k in brackets to the power n converge? Well, for convergence, we know the ratio needs to be greater than -1, less than 1. It needs to be in between there, or it needs to be just a normal fraction, a proper fraction, in the form a over b, where a and b are integers, and a needs to be less than b. So that's just spoken mathematically. Yeah, seem to be going off screen here. Let's see if I can. That's cuter. Nice on the fly editing. Okay, so what's happening here? Well, we know what the sum to infinity's formula looks like. Let's get a 1 minus r. But what we're interested here is only r. So for that we need t2 over t1 at the very least, and that's quite easy to calculate. So let's have a look at it. So we'll have t1 being equal to 3 over 2 minus 1, no, minus k to the power 1, and then t2 will be equal to, well, 3 over 2 minus k to the power 2. Therefore, t2 over t1, we can do that in a different color, is going to be equal to 3 over 2 minus k squared, all divided by 3 over 2 minus k to the power 1. Well, that cancels, and we have 3 over 2 minus k. Well, that's our r value, or our common ratio. Now, for which values of k will this be? A convergent series. There's the inequality we used to set this up. So quite simply, 3 over 2 minus k should be less than positive 1 and greater than negative 1. So first step, just subtract 3 over 2 right through. So minus 1 minus 3 over 2. That just becomes negative 5 over 2. Less than negative k. And then 1 minus 3 over 2 becomes negative half. Now we need to be careful. We are going to multiply by a negative right through, so that will turn k positive. Okay, so if we multiply by a negative over here, if we multiply by a negative over here, well, this becomes positive 5 over 2. And I think everybody knows why I am writing this on the right hand side instead of on the left hand side. And then that becomes positive 1 over 2. Because this entire thing needs to flip. Because I am multiplying by a negative. But if I switch these two terms around, I am allowed to maintain that thing, thus giving the flip and acknowledging that I have changed my inequality signs. However, that's what that boils down to. And in a sense, if you regard maths as a language, this is one of the parts where it just requires an extra bit of depth in the form of literacy. Being able to read sigma notation for what it is. It's just a summary. And it gives us summation sigma, so all the s's over there. Now, well, this one I thought was cute as well, just because of its structure. If you can look at this, it's just consecutive terms being added up, and there's a pattern to this. So it's the first two numbers, first two whole numbers, first two positive counting numbers, added up, that gives us 3. Then if you want to maintain, you have to do the next 3 counting numbers, and then 4, and then 5, and so on. But this creates something interesting. Well, that's 1, that's 4, that's 9, that's 16, that's 25. Well, anyone with a more than passing interest in numbers will notice something about these. They just happen to be perfect squares, which is why they can give this instruction: write down the first term of the 20th row. Well, that's just going to be equal to 20 squared, which is equal to 400, because that's the pattern that emerges there, and it's long enough so that it should be maintained because of this word, etc., etc., etc. It's just Latin for and so on. Determine the term that appears immediately after the equal sign in the nth row. Well, first let's just locate this term. Well, it's 3, and 7, and 13, and 21, and 31. Okay, so that's 3, 7, 13, 21, 31. See what this does. That's 4. 13 minus 7 is 6. 21 minus 13 is 8. 31 minus 21. Ew, that's 10. This looks very familiar. Oh, we have a constant second difference. Well, quadratic pattern solvers unite, because 2a is equal to 2. Lastly, a is just equal to 1. Well, then 3 times a, which is 1, plus b is going to equal what? That value over there, which is 4. Subtract 3 on both sides. B is just going to equal 1. And then for that one, we know that's a plus b plus c equal to 3 in this case. And what do we have? 1 plus 1 plus c equal to 3. That's 2, which we want to subtract on both sides. Therefore, c is also equal to 1. Well, that's cute. Therefore, dn, the general term, or the the term after the equal sign in the nth row over there, which is some sort of general term, is just going to be equal to, well, according to this, n squared plus n plus 1. Makes sense, because in this row all we had was n squared. Makes sense that that would sort of carry over and become some sort of quadratic pattern as well, just augmented, as we can see. Next, well, this one's cute. If x multiplied by log base a square root of a plus 1 is equal to 3x, we need to solve for x. Let's just reset up this equation in my not so pretty handwriting. It's log a square root a plus 1, that's all equal to 3x. Well, let's sort out this weirdness over here. So that's just going to be, well, log base a to the power 1 over 2. Well, now we can multiply by our x plus 1, still equal to 3x. Oh, where does that leave us? Well, we know the exponent on the argument. A is the argument. Well, technically, let me restate that. If the entire argument of a log, this part on the inside, has an exponent on top of it, we can take that exponent and transfer it to the front and make it a product with a log. Remember, the only thing a log is another way of writing an exponent. In fact, it's useful to remember that the answer to a log is an exponent. Hence, we can rewrite this as 1 over 2 multiplied by x multiplied by log base a of the argument a plus 1 is equal to 3x. Now remember, keep your arguments on the inside. Radio. Let's move to where there's space, because now we'll have 1 over 2x. Well, if the base and the argument are the same, that means that entire log is equal to 1. So I didn't cancel it, it's equal to 1, and 1 times a half x is just 1. Well, other than that, we can transpose the 3x by subtracting it on both sides. That zeroes out, so we'll have minus 3x. And then we'll subtract 1 on both sides. That zeroes out. And everything will be equal to negative 1. Well, this now becomes pretty easy. So we'll have negative 5 over 2x being equal to negative 1. Well, multiply both sides by negative 2 over 5. And x will be equal to 2 over 5. That's good. No fear from seeing logs. No fear whatsoever. So, f of x in this case is equal to 2x cubed plus ax squared minus b squared x minus 3. And then we get given a scenario. Let's see. If f of x is divided by x plus 1, the remainder is 9. And f of x is divided by x minus 1, the remainder is negative 5. So let's deal with the first remainder and divisor. Okay, so we have a divisor of x plus 1 and a remainder of 9. Written in functional terminology, the value we are investigating here is negative 1. So we'll have f of negative 1 being equal to a remainder of 9. So that gives us something to work with. So by the same token then, if the factor is x minus 1, then the value of x we are investigating is 1, and that remainder is negative 5. So that's a bit easier to deal with, because we know what to do with these. that just sets up equations where we substitute the x value on the right hand side, and we acknowledge the right hand side, the 9 value, the remainder, by substituting it for the entire y value on the left. So let's do that. So for the first one, I think we'll choose blue. We have 2 times -1 all cubed plus a -1 all squared minus b squared, and that's still multiplied by -1 minus 3, and that's all equal to 9. Well, that's just -2, negative times a negative is positive, and that's just a -1. Over here we'll have a negative times a negative. Let's add it up. It's b squared. We'll have -3. That's all equal to 9. So let's see. Well, that's -5. It gives us -5. We collect them. So now we can add 5 to both sides, and we'll have a plus b squared is equal to 14, and let's just label that equation as 1. Well, let's tackle this one now. So that one's hopefully even simpler. Plus a times 1 squared minus b squared times 1 minus 3. Well, that's equal to -5 over there because it was running out of space on the right hand side. So let's just sidestep that problem. So -5 is equal to, well, that's 2 plus a, so it becomes minus b squared, and we'll have -3. 2 and -3 is -1, and then we want to add 1 on both sides. 0 this out, it's 1. So -4 is equal to a minus b squared, and we'll call that equation 2. That's our label. So what can we do with those? Well, that's magic. Let's do that. I can move it slightly better, I think. There you go. Let's just move that way, and remember what our value was. That was equal to 14. Maybe I should write it in blue. Just acknowledge what it was. Okay, and our label to that was 1. So for these two equations, we can see if we add up the b squareds from equations 1 and 2, they'll 0 out. So why not just do that? 1 plus 2. So now we'll have 2a on the right hand side, and on the left hand side we'll have 10. Therefore a is going to equal 5. And if we take this value and sub it, where is this going to be easier? Into 2. So we'll have -4 equal to, well, a is equal to 5 now, minus b squared, and we should have, well, -9 minus b squared is going to equal -9. See where we can find a little bit more space. Multiply by negative both sides, and b squared is equal to 9. Therefore b is equal to plus or minus 3. I think that's good. So based on the way that this function operates, either value should be just dandy, because we are squaring that b inside the function in any case. Not doing that. Adio. How about this one? This one's interesting. Well, just because of the use of b. Well, first things first, calculate the average gradient between where b is equal to -1 and b is equal to 2. Okay, So we need to find the requisite y values for these, and as we can see, this is the intercept form. If we make p equal to -1, in this function we'll get a 0, and over there we'll get 0, so this will end up being 0 minus 0 over, well, 2 minus -1, and that's just 0. So that's equal to the average gradient over there. Determine a formula for the gradient of f using first principles. Well, we don't have a product rule, so let's just multiply that out, because we can say then that f of p is equal to p squared. Well, minus 2p plus p gives us minus p, and then minus 2. So then we'll have f of p plus h. So that's p plus h all squared minus p plus h minus 2. Let's see what that simplifies to. P squared plus 2ph plus h squared minus p minus h minus 2. And then like terms to collect, none whatsoever, not a single one. Let's see. Yeah, we need to make this slightly smaller. Yeah, that just created some space for us. Wonder of cutting and pasting. Can also move this. Yep. And shrink. Good. So, remember, we'll have f prime of p, which might be a little bit weird, but that's just a question of making sure we make adjustments to our formula. And that's just turning the x's into p's. So it's p plus h and f of p all over h. Well, that acknowledges first principles, but instead of an x we have p. Well, what do we have here? Well, I feel we can subtract this over here. P squared minus p minus 2. That's going to 0 out. Those two are going to 0 out. Those two are going to 0 out. And we would be left with, well, 2ph plus h squared minus h, which is a lot easier to deal with. Also, that's perfectly legal to do it off to the side. So we'll have 2ph plus h squared minus h over h. And why would it be legal to do it off to the side? Well, this is just all you're doing over here is compartmentalizing everything. As long as it's done neatly, okay, either before we do this or slightly off to the side, it's showing your calculation as required by the instruction and information sheet at the front of the paper. Well, over here we can just do this. Take out the common factor as per usual. So it's 2p plus h minus 1 all divided by h is equal to 1. And as soon as we substitute, we can drop the limit notation. So that'll be 2p plus, let's acknowledge the substitution, minus 1, and that's 2p minus 1. And just for funsies, we can double check over here. If we have p squared minus p minus 2, obviously f of p and f prime of p, just using our differentiation rule, the power rule. Well, 2 times 1 is 2, and then 2 minus 1 in the exponent gives us just 1. Check, and then that's, well, given that exponent is 1, that's just going to be -1. Done and done, as they would say. Space required, space required, space required, space granted. Let's get a pin back. Feeling pink for this next one. calculate the average gradient of f. Calculate the gradient. Almost read that wrong. Calculate the gradient of f at p equals -1 and p equals 2. Well, f prime of -1 is going to come from, what did we say? F prime of p from first principles turned into 2p minus 1. So that's just going to be equal to 2 times -1 minus 1. So that's equal to -3. And then f prime of 2 is equal to 2 times 2 minus 1. And that's just equal to 3. So now we have the instantaneous gradients at these 2 points. P equals 2, sorry, and p equals -1. And where do I get an instantaneous gradient from? From the derivative of the function. Derivative is nothing other than an instantaneous gradient. Well, determine the points of intersection of the gradients of the graph of f at p equals -1 and p equals 2. Now first things first, we have a gradient over here which is an m value, and we have a gradient over here which is an m value. So let's just write them in as such. We'll call them m at -1 and this is m at 2, obviously. So we have those two gradients sorted. Well, now we need their straight line equations. Why? Because they want a point of intersection for those tangents. Well, other than that, we have the x values for the points of contact. We need their requisite y values. So let's just bring f of p back in its required form, standard form. Squared, what do we say, minus p minus 2, obviously. So we need f of -1 is going to equal -1 all squared minus 1 minus 2. Well, that's +1. That's also +1. So 1 plus 1 minus 2, that's equal to 0. How about f of 2? Oh, my 2's are looking ugly this year. Well, not that they were much better last year, or the year before, or the year before, or the year before. Well, that seems to be true as well. 2 squared is 4. Yeah. Minus 2. Well, we have 0. So, which points do we have? -1 and 0. And then we also have +2 and 0. No, actually, no, it's not. Well, for that, we are now going to use that gradient, and for these sets of coordinates, we are going to use that gradient. So using y is equal to mx plus c, let's just substitute our values in. So we'll have 0, gradient is -3, x value is -1, mx plus c. Therefore for this one, c is equal to -3. For the second one, we'll have again 0 is equal to 3 this time. Our x value is 2 plus c. Therefore c is equal to -6. Therefore we have two equations. For this one, we'll have y is equal to I can write that better. So over here we'll have y is equal to -3x minus 3, and for the second one we'll have y being equal to, well, 3x minus 6. Now to get our point of intersection, we'll need to equate those two equations or make them equal to each other to see where they go through each other. So we'll have -3x minus 3 being equal to 3x minus 6. Well, 3x on this side, minus 3x on that side. So we have minus 6x plus 3 plus 3. That zeroes out, and we'll have minus 3 minus 3. So dividing both sides by negative 6, we'll get x being equal to 1 over 2. And we can use any of the two equations to get the other point. So we'll just say y is equal to 3 times 1 over 2, given that we're in white. In terms of the chalk color, minus 6. So that's 3 over 2 minus 12 over 2 is minus 9 over 2. Negative 9 over 2. We're giving us our coordinates of 1 over 2 and negative 9 over 2. Show that this point lies on the axis of symmetry of F. So let's leave the point over there. And let's just understand what an axis of symmetry is and what it does. Well, the normal formula that we use, or generally use, would be that P is equal to minus B over 2A. However, in any parabola, regardless of where it sits, the axis of symmetry is always right between the two x-intercepts. So if we know the two x-intercepts, we can just apply something that's very similar to the midpoint formula. So we'll have P is just going to equal, well, in this case, what's our values? Minus 1, which comes from that intercept, plus 2, which comes from the intercept created by that factor, and then we divide that by 2. We'll see over here is, well, minus 1 plus 2 gives us 1 over 2. And then we need to substitute this value into the equation, and we should be getting negative 9 over 2. I'm going to sound like a professor now and say that exercise is left to the student. Well, and that's the end of something that was hopefully mildly interesting and displayed a couple of interesting questions, problems. Good luck. Breathe. And be awesome tomorrow.